Hey everyone, welcome back to our last lesson for the exponents and logs unit. We're going to be looking at lesson 5 in the workbook and also some work out of the some examples out of the textbook. So we're looking at logarithmic scales and applications of those, and we have in that category we've got 3 such examples of earthquakes. We have pH, we have the measure of sound, decibels. Okay, all of those are logarithmic scales. And really it's a way to kind of make really large numbers or really small numbers a little easier to deal with. So the Richter scale, which is a way to measure earthquakes, is named after this guy, Charles Richter, yada yada. And basically this Richter scale, the difference between 9 and 8 on the Richter scale is a magnitude of 10. So it's a 10-fold increase in intensity when you change by 1 unit on the Richter scale. So if you were to go from a Richter scale, a magnitude of 9 to 7, that's actually 10 times 10, or 10 squared as intense. Now, where does it all start? Well, a magnitude of 1.0 on the Richter scale is equivalent to a large blast at a construction site using approximately 14 kilograms of TNT. Interesting. And that would be 10 times as intense as the 0 reference point. So an earthquake with magnitude of 2, or 10 to the 2, times as intense as the reference point of 0. Okay, so any earthquake above 6 is really considered dangerous. Largest yet recorded is the Chilean earthquake of earthquake of 1960. Registered 9.4 on the Richter scale. Wow, that's pretty big. Yep, and they've got that one up here. Oh, they've got 9.5 here, so maybe they meant 9.5. Okay, and in North America, the largest earthquake recorded is one in Alaska in 1964, measured 8.4. Okay, so example number 1 is just a way to kind of use that scale. An earthquake in magnitude 8 would be 10 times as intense as an earthquake of magnitude 7. Okay, now if we were to go from a magnitude of 7 to a magnitude of 3, that's 4 units on the Richter scale, so that would actually be 10 to the 4, which is essentially 10,000 times as intense. Okay, if we were to go from magnitude of 4, compare that to a magnitude of 6, that would actually be less than 1, so 10 to the negative 2, or 1/100th times as intense. The negative 2 came from going 4 minus 6. Okay, so you kind of get the idea of these, right? So we're going to take a look at the next page. So this skill here with comparing earthquake intensities is one that you need to know how to do. Basically using a basic function that they may give you, come up with kind of a new formula. Okay, that might be something that they test for on the diploma. So basically to compare intensities of magnitude M1 and M2, let's say, 2 different earthquakes, the magnitude of an earthquake is actually given by this formula here, where I is the earthquake intensity and I naught is your reference intensity. Okay, so we have M1, let's say, earthquake 1 would be equal to log of I1, the intensity of that earthquake, divided by the reference earthquake intensity. Okay, so what they want us to show on this first one, show that M1 minus M2 is equal to log of I1 over I2. Well, let's try that out. First of all, we could replace M1 with what it equaled, right? So we could replace that with log of I1 over I naught, or I subscript 0, minus, and M2 is equal to log of I2 over I naught. Okay, now let's work with that and see if we can get it to look like the right-hand side of the equation. Okay, let's think. We're subtracting 2 logs. They're both base 10 because there's no base written. So we could use our quotient law for logarithms and write that as dividing within 1 log. So I1 divided by I naught over top of I2 divided by I naught. Okay, so you remember the old saying, dividing by a fraction, same as multiplying by the reciprocal. So that would become I1 over I naught times the reciprocal of what's on the bottom, so I naught over I2. And then we can reduce any common factors. So I naught could cancel, and then we could simplify, write that together, and that would be the log of I1 divided by I2. And there we go, we proved it. So that's equal to the magnitude of the first earthquake minus the magnitude of the second earthquake. Now part B, they're having you, so it says hence show that I1 over I2 is equal to 10 to the m1 minus m2. So what we could do is take this equation, log I1 over I2, and we could basically isolate the I1 over I2. So how would we do that? We need to get rid of the log then. So we are going to write it in exponential form, or exponent both sides. The base on the log was 10, that's why you use 10 to the... Okay, so now we have I1 over I2 equals 10 to the exponent of m1 minus m2. And there we go. We have shown that that is equivalent to that. And we're going to actually use that. We're actually going to use that, sorry about that interruption, in our calculations for the examples below. Okay? So how many more times intense was the 1960 earthquake, magnitude 9.5, than the 2005 earthquake, magnitude 7.8? So when they say how many times more intense, they're looking for this ratio. So we're not trying to find I1 individually or I2 individually. We're just trying to find the ratio of I1 over I2, and that's how many times as intense it would be. Okay, now the first earthquake they mentioned was 9.5, so we go 9.5 magnitude minus 7.8 magnitude in the exponent, base 10 there. And then it's just calculate or work it after that. So grab your calculator, let's see if we can get a number. They want to the nearest whole number. Okay, just make sure you have brackets around your exponent, otherwise you'll only be going 10 to the 9.5. Okay? Okay, so we should have in our calculator got approximately 50.118 yada yada. So to the nearest whole number it would have been 50 times as intense. Okay. Now, other way we could turn this one around is with example 3. A major earthquake of magnitude 7.5 is 375 times as intense as a minor earthquake. Find the magnitude of the minor earthquake. Okay, so what they're giving you here by saying 375 times as intense, they're giving you in this equation the, they're giving you the I1 over I2. So that is your 375, okay, equals 10 to the, and then the minor earthquake is the one we're looking for. Now because 375 is bigger than 1, the larger earthquake has to go first and the smaller one second. And now we want to solve for m2. So m2 is in the exponent, so we're going to log both sides. Log 375 equals log 10 to the 7.5 minus m2. Now, since it's base 10 and it's based on the power inside the log is also 10, therefore that would just equal the exponent. So we'd have log 375 equals 7.5 minus m2. And then because this m2 is negative, I would actually suggest that we add m2 to both sides, and that will eliminate us having negatives later on. So we would have m2 plus log 375 equals 7.5, and then subtract log 375. Okay, so 7.5 minus log 375. Okay, off to the calculator. Let's see what we get for that magnitude. Okay, so we should have gotten 4.92 yada yada, and they want to the nearest tenth, so that would be 4.9 magnitude. And notice that's less than the 7.5, so that does make sense. And really, 375 times, right? 4.9, and then 5.9, 6.9, so that would be at 6.9, that'd be 100 times more intense. So we're a little more than that, and that makes sense that it would be 375. Good, let's look at the next page. Okay, so another decibel or logarithmic scale is the decibel scale. Technically, not really the decibel scale, but the Bell scale is a logarithmic scale. A decibel is basically 1/10 of a bell. Okay, so decibel is 1/10 of a bell. So if you want to work like we did with the Richter scale, we actually need to change it to bells first and then work as we did before. So if we were to look at example 4, a power saw, 120 decibels, is how many times as loud as a telephone dial tone? Well, if we change 120 decibels to actually 12, divide by 10 to get it into bells, so 12 bells, and then change 80 decibels into 8 bells, that means they are a distance of 4 on the logarithmic scale, which is basically 10 to the 4 times as loud, or 10,000 times as loud. Okay, so you get the idea with that one. Same as the Richter scale once you change it into bells. Okay, let's look at the next page. Okay, so on the next page, they talk about for decibels, and they have a formula for that, but you know what? It's just easier to work in bells, make sure things are in bells, and then we can use, look at this formula. Doesn't that look exactly like the formula for Richter scale, except it was M1 minus M2? So it's really the same formula, and we can just use that if we have any questions on it. Okay, example number 5, given that decibels equals 10 log, so they're giving you an equation, and this could happen on your test or on the diploma as well, where they hand you an equation, and then you just have to work with that. Show that the decibel level for the threshold of pain, okay, 125 decibels, so, and given that this is decibels, we don't need to convert that for this one, has a sound intensity, okay, which is the I, of 10 to the 12.5 I naught. Okay, so all we have to do really is replace the 125 in for decibels. So we would have 125 equals 10 log of I over I naught. And our goal is to isolate I. So let's think about this. First we want to isolate the logs. We're going to divide both sides by 10. Okay, which would give us 12.5 equals log I over I naught. Then we want to get rid of the log, base 10 on the log, so we're going to put it in exponential form or exponent both sides. And there we go. Now we have 10 to the 12.5 equals I over I naught. Last step, multiply both sides by I naught. So multiplying by I naught, we'll get rid of that. And then you'll take a look and we have I equals oh, they put that at the end. Okay, so we'll write it as 10 to the 12.5 and then I naught. And there we go. We showed that the intensity was equal to that. Okay, let's try example 6. How many times more intense is the sound of playing a piano? 67 decibels. So let's write that as bells, because now we're going to be using the same, you know, I1 over I2 equals 10 to the M1 minus M2, that formula. Okay, so 6.7 bells versus 22 decibels, so 2.2 bells. Okay, so we just simply need to put those in. 6.7 in for M1, 2.2 for M2. Grab your calculator and probably round to the nearest whole number. Okay? Okay, pretty significant difference. It seems we got 31,622. So it's about 31, and that'd be 23. 31,623 times as loud. Wow, that's significant, isn't it? Playing the piano versus whispering. Holy cow. Okay, so example number 7, we're going to skip, and we'll take a quick look at the next page. Okay, pH scale is also a logarithmic scale. Very similar. It can get a little bit trickier because the word acidic versus alkaline is used. Acidic is down at the bottom of the scale, like pH of 1 is acidic, and then alkaline is up near the top of the scale. So let's look at there's any examples to do on this one. We're going to skip example 8. Okay, so we're going to look at example 10 and 11. The pH of the solution is defined as pH equals, and if you're doing chemistry right now, you might actually recognize that formula. pH equals negative log H plus, where H plus is the hydrogen ion concentration in moles per liter. Okay, I'd like you guys to try example number 10. Actually, we can start that together, but we're going to run out of time, so we'll continue this in part 2. Okay, so urine sample, lovely. Okay, pH of 5.7. What was the hydrogen ion concentration? So you just simply sub into the formula that was given above, and you solve for H plus. So in part 2, we'll go over the answer of that. So why don't you give that one a try? Okay, and then I'll see you in part 2.